Well, it's really marvelous. It's very gratifying to realize that a idea and a theory that we worked on nearly 50 years ago has such huge relevance to actual physics. When we started working on this model, in fact, much of the original work comes from my PhD thesis at Harvard, and in fact that's when I started talking to Professor Hagen. But when we started working on it, we had no idea that it would be more than an interesting model. But when we finally solved it, working with Professor Kibble, we knew that we had indeed done something that was very different and was very exciting, but we still didn't expect it to have anything to do with physical reality. After the unification work of Weinberg and Salam, we knew that really there was something that was probably very right about this model. And now these wonderful results of today all but make it certain, I think. It's very gratifying to know that model really was right. And it shows, certainly to us, the value of just imagining and just asking, just trying to follow the leads that you get from simple ideas, that it's worthwhile doing this and seeing where you come out. It was really fun for us, and now we see that something really important has happened from those ideas. What we did was to follow up on the ideas of symmetry breaking that were first introduced by Nambu. And it started with my PhD thesis at Harvard, where there was a question of how the ideas of symmetry breaking could be applied to a model that looked like the electromagnetic field. And at that stage, there was a general theorem that seemed to show, and in fact does show if the theorem is applicable, now called the Nambu-Goldstone theorem. This theorem showed that if you looked for the so-called symmetry breaking solutions of the model, solutions which were fundamentally different than the coupling constant perturbation theory solutions which were used at the time, that if you did that, the price you paid for studying symmetry breaking was that there was a massless physical particle. And what we did, which evolved from work done by Schwinger and later by Bowler and Gilbert, was to show that there was a model that starts out looking like electrodynamics coupled to scalar fields, but that model had other solutions than the only known ones at the time, which were based on perturbation theory. And in fact, this is a general characteristic of all quantum field theory models, but we didn't have that understanding at that stage. We didn't really appreciate the importance of the nonlinear nature of these models. But what we discovered was that there were other solutions to ordinary electromagnetic action, and that those other solutions were fundamentally different, and that those solutions, even though they came from a symmetry breaking of the original model, that those solutions did not have a massless boson. And in fact, what was astonishing is that the massless particle that would have normally been the photon in the normal theory acquired mass, and the degrees of freedom were rearranged so that normally the 2 degrees of freedom of the photon combined with 1 degree of freedom associated with the scalar field to form a massive particle. And the remaining degree of freedom is, of course, what's now known as a Higgs boson. And we developed that entire theory. We were amazed at the results. We were told that we were wrong. I was even told, I don't think Professor Hagen actually heard the conversation, but I was told by Heisenberg that I was wrong, which was pretty scary for a young man who wanted to get a job. But we very carefully studied the theory. We were convinced when we published it that we had covered all possibilities that we understood of the theory being wrong. We had done many consistency checks, and we were sure it was right.